are discussing the working principle of a multi-layered feed-forward neural network. Now, supposing that I have got a process whose input output modeling has to be done. That means, for a known set of inputs, what should be the set of outputs that we will have to determine. Now, the first thing we will have to do is, so we will have to identify the input parameters and the output variables. Now, these input parameters are to be independent and they should be measurable. Now, here if you once again see the schematic view of this multi-layered feed forward network, we can see that. So, this is the input layer through which we pass the set of inputs, and these inputs are to be in the normalized scale, either in the scale of 0 to 1 or from -1 to +1. Now, how to represent in the scale of 0 to 1 or -1 to +1? So, that I have already discussed. And here, so this is nothing but the output layer, and on the output layer say we have got say p number of neurons. Now, these output could be either independent and they could be dependent on each other also. Now, here you see the connecting weights between the input and the hidden layer is denoted by V, and that between the hidden and the output layer is denoted by W. And we have already mentioned the range for the connecting weights could be either from 0 to 1 or from -1 to +1. Now, here for this particular process, the number of inputs, that is m. Now, this is kept fixed, and similarly the number of outputs of this particular process. So, that is also known. So, the number of neurons in the input layer, that is nothing but the number of input parameters, and the number of neurons on the output layer is nothing but the number of outputs. So, the number of neurons in the input layer and the number of neurons in the output layer, those are known, those are kept fixed. Now, the architecture of this particular network depends on the number of hidden layers and the number of neurons you put in each of the hidden layer. Now, here you can see for simplicity, so we have considered only one hidden layer, and this hidden layer is having say capital N number of neurons. Now, how to decide the number of hidden layers, or how to decide this particular the architecture? So, that I am going to discuss little bit. Now, before I start that, let me mention that there is no guarantee that we can ensure more accuracy of this particular network by increasing the number of hidden layers. That means, if I use say one hidden layer for modeling input output process, and using the same training set, if I develop another network having say two hidden layers. Now, the network having two hidden layers, actually we cannot give guarantee that it is going to give more accurate predictions. Now, how to decide? Now, to decide this, actually what we do is, the first thing we will have to decide that what should be the minimum number of neurons in this particular the hidden layer. And let me assume that there is only one hidden layer, and the minimum number of neurons to be put in the hidden layer is equal to 2. The reason is, if we do not put the minimum number as 2, we may not be able to capture the nonlinearities of this particular the process. So, to capture the nonlinearity of this particular process, the minimum number of neurons to be put in the hidden layer is equal to 2. Now, what should be the optimal number? What should be the optimal number of these particular neurons in this hidden layer? Now, to decide that, actually we will have to carry out one parametric study. Now, before I go for discussing the method of this parametric study, let me once again mention that the performance of this particular network depends on a number of parameters. Of course, it depends on the connecting weights, that is V and W. Now, besides this particular the V and W matrices, the performance of this particular network depends on the number of the neurons which we are going to put in the hidden layer, that is denoted by capital N, or the number of the neurons we put this particular the hidden layer, that is N, and it depends on the bias value. Now, for simplicity we have not shown the bias value, but it depends on the bias value. Now, if you want to put the bias value, so we will have to put that particular the bias value. So, I can put this particular the bias value here. It depends on the coefficient of transfer function, that is A 1, that means your this log sigmoid transfer function. It also depends on the coefficient of transfer function of the output layer, that is nothing but A 2 and so on. So, these are the parameters for which we will have to determine the set of optimal values. Now, to carry out this parametric study, actually what we do is we first try to fix the range of each of these particular the parameters. For example, to fix the range, the minimum number is 2. Now, supposing that I am just going to put the range for n is say 2 to say 20. Now, I can also put the range for this particular b. So, might be it is 0.001 to say 0.01 something like this, and for this A 1 and A 2 I can also put the range. So, might be it is 0.5 to say 5.0 and so on. Now, once we have decided these particular ranges for the parameters, now we are in a position to start the parametric study, and the purpose of parametric study is to decide what should be the topology of this particular network and what should be the parameters, the other parameters. And let me repeat that these connecting weight values, those are generated in the normalized scale using the random number generator. Now, let us see how to carry out this particular the parametric study. Now, the first thing we will have to do is we will have to vary the number of the hidden neurons starting from 2 to 20 say, and regarding the other parameters like your B, A 1 and A 2. So, we try to find out their mid values, and these parameters are set to their corresponding mid values, and I am just going to vary the number of neurons to be present in the hidden layer. Now, if I carry out this particular study, so there is a possibility that I will be getting. So, this type of your the study, the results of the study. So, what I can do is I can plot say the error of this particular the network, that is error in prediction, and here we have got the number of neurons to be put in the hidden layer, and we keep some fixed value for say V, we keep some fixed value for A 1 and A 2. Now, what I do is we start with the 2 number of hidden neurons. So, say supposing this is going to indicate 2 number of hidden neuron. So, I will be getting some error. So, error could be here. Then I use like 3 number of hidden neurons, might be the error could be here. Then I use the 4 number of hidden layers, might be the error could be here. So, what we do is we try to find out the nature of the performance of this particular the network, and then we try to select so that number of hidden neuron which gives actually the optimal performance in terms of error in prediction. Now, supposing that this is the number of neuron corresponding to which I am getting the optimal performance. Now, what we do is the value of n is kept fixed to this particular value, and next we go for the variation of this particular the b. Now, what we do is, so exactly in the same way, we carry out the study. So, now here there will be error and here there will be the bias value, and n is kept fixed to the optimal value which you have already determined in the previous step, and a 1 is kept fixed to its mid value, a 2 is kept fixed to its mid value, and once again for different values of b. So, we try to find out the error and we try to locate that value of b corresponding to which we are getting the minimum error. So, we select the near optimal value for this particular the b. Next, we start this particular study by varying this particular a 1 and we try to find out what should be the optimal or the near optimal value for this particular a 1. Next, we start this particular study actually with the variation of this particular a 2 and we try to find out what should be the near optimal value for this particular the a 2. So, by carrying out this particular study, so we can find out what should be the near optimal value for this particular the number of hidden neurons, what should be near optimal value for this particular the bias value, then comes what should be the near optimal value for this a 1 and the near optimal value for this particular a 2. And once we have got this particular thing, now we are in a position to decide at least approximately what should be the topology of this particular network and what should be the other parameters. Now, here I just want to make a comment. This process of carrying out the parametric study is an approximate one, because here the performance of this network depends on all the parameters simultaneously, but what we did is we consider one parameter at a time. That means, this is an approximate way of determining the near optimal parameters of this particular the network. So, this is the way actually we can approximately determine like what should be the topology and what should be the other parameters for this particular the network. Now, as I discussed in my last lecture that this particular network has to be trained, and if I go for the supervised learning. So, this supervised learning actually it can be implemented either in the incremental mode of training or in the batch mode of training. Now, I am not going to repeat, because this I have already discussed in much more details. The principle of the incremental training, the batch mode of training, their relative merits and demerits, those things we have already discussed. But now, I am just going to concentrate little bit on the batch mode of training for this supervised learning. Now, supposing that in batch mode of training, say I have got a large number of training scenarios, say capital L number of training scenarios, and as I mentioned several times. So, out of this capital L, the first one I am just going to pass, and depending on the connecting weights, the coefficient of transfer function and other things. So, I will be getting the set of outputs. Now, this set of calculated outputs will be compared with the respective target values just to find out the error. And once you have got error at each of these particular output neurons, so I can find out what should be the combined error, and that corresponds to a particular the training scenario. Then we take the help of the second training scenario, I will be getting another the total error here. Then the third one, fourth and I just go for the Lth training scenario. And once I pass this all L training scenarios, I will be able to find out what is the total error, what is the average error, and based on this particular error. So, I will have to propagate back, so that I can modify the different the variables, and ultimately through a large number of iterations I get that particular optimal or the near optimal network. Now, here I just want to make a point, like if I just go for the batch mode of training. So, we will have to be careful that we have used sufficient number of training scenarios. Now, supposing that, so this particular network is having say approximately, let me consider, it is having say 100 design variables. Now, if it is having 100 design variables or your parameters which can be optimized, whose modified values can be determined. So, what I will have to do is I will have to pass at least 100 training scenarios. So, either 100 or slightly more than 100 training scenarios I will have to pass while carrying out the batch mode of training. Now, let us see what happens if I just pass say less number of training scenarios. This I have already mentioned, and let me try to repeat once again. Now, supposing that I have got 100 design variables. Now, if I pass say 90 training scenarios, that is a case of the under training of this particular the network. That means, mathematically if you want to put, supposing that I have got 10 unknowns and I have got say 9 equations. So, if there are 10 unknowns and 9 equations, we cannot solve it mathematically. The same thing is true here. If I have got less number of training scenarios compared to the number of unknowns, this will be a clear example of your under training. And if there is under training for this particular network, and if I pass say set of inputs, we will be getting some output, but this particular output cannot be actually believed, and this network actually does not know anything of the physical problem. So, if we just pass say one set of training scenarios, we are going to get the outputs for a set of inputs, but this particular input output relationship may not be reliable. Now, on the other hand, if I use a very large number of training scenarios and if I train this particular the network through a large number of iterations. Now, let us see what happens. Now, if I just train this particular network for a large number of iterations using a very large number of training scenarios, supposing that I have got only 100 design variables, and if I use 1000 training scenarios and I train this particular network for a very large number of iterations, say 5000 iteration, what will happen to this particular the network? Will this network is going to give a very good performance? The answer is no. Now, here there will be some sort of overtraining. So, this overtraining is also actually is not good for this particular the network, and the reason I am just going to discuss in details. Now, if there is a overtraining, this particular network will try to remember actually the training scenarios, and what will happen the moment we pass the unknown test scenarios, it will try to remember only the training scenarios, and it may not perform in the optimal sense for the unknown test scenarios, because its adaptability will be lost or its generalization capability will be lost if I just go for the overtraining. Now, as I told that this particular should have a very good generalization capability. So, this generalization capability is actually a desired property for this particular the network, and if we want to ensure. So, what we will have to do is, so we should not go for undertraining and we should not go for overtraining, and in other words actually we should go for a perfect training for this particular the network. Now, supposing that, so we have selected the number of training scenarios, the required number of training scenarios for carrying out the batch mode of training, and while carrying out this particular batch mode of training. So, there is a possibility that we may face another problem. Now, that problem actually I am just going to explain, and this I have learned from my own practical experience. So, this I am going to discuss. Now, supposing that I am carrying out the batch mode of training for this supervised learning, and I am using the suitable number of training scenarios, and I am using the generalized delta rule, the back propagation algorithm, that is nothing but supposing that I want to update this particular the connecting weight. So, what I will have to do is, so delta W j k at the tth iteration is nothing but is your minus eta multiplied by the partial derivative of your say E k with respect to say your delta W j k plus alpha prime multiplied by your delta W corresponding to your t minus 1th iteration. This is actually the generalized delta rule. So, this is your generalized delta rule. This I have already discussed. Now, using this generalized delta rule, I will have to update this connecting weights, and I have already discussed the eta is nothing but the learning rate, and it has got the range 0 to 1. Then alpha prime is nothing but the momentum constant, and the purpose of using the momentum constant I have already discussed. If you want to provide some sort of damping effect to the network, and if you want to provide some sort of cushioning effect to this particular the network. So, we will have to use this particular your momentum term. Now, here there is one mathematical reason why do you put this particular your the momentum term. Now, supposing that the way we update this particular network is nothing but W j k updated is nothing but W j k the previous value plus delta W j k. So, this is the way actually we update. Now, supposing that, so this particular delta W value is found to be positive for a large number of iterations, consecutive iterations. Now, this delta W it could be either positive or negative, but fortunately or unfortunately say I am getting the positive value for a large number of consecutive iterations. Then what will happen to this particular your delta j k updated? Now, there is a possibility that this particular delta W j k will come out of the range. That means, it will become say greater than 1. Supposing that this is becoming W is becoming say 1.5, whereas the maximum limit for this W is say 1. Now, what will happen to this particular network? Now, as I mentioned several times, that network does not know anything of the physical problem. Now, even if the W has come out of the range or the V has come out of the range, if you pass this set of inputs, the network is going to give you the output, but that particular output may not be reliable, because so this particular connecting weight values have come out of the range, and if this is the situation, so that particular situation is actually known as actually your that instability problem of this particular network. That means, the network has become unstable, it has lost its balance, and so this particular network is going to behave in a very the erratic way, and you may not get a very good prediction for a set of inputs. Now, here we can put one remedy. The remedy is something like this. So, if W or V becomes greater than 1, so it has become out of range. So, what we do is in place of V, so what we put is, or in place of W, what we put is 1 divided by W, or in place of V you put like 1 divided by V. So, by doing that, actually what you can do is, So, W become greater than 1. Now, 1 divided by W will be less than 1, same is true for your V and 1 by V, and by doing that once again forcefully we are going to put that particular limit within the range, and what will happen is your this network once again will try to become stable. But if you see this particular performance, like if I just say this is error, and what will happen is the moment you put this particular correction or this particular correction, so there will be abrupt change of this particular performance, and after that it will reach one stable region. And once again if it becomes out of range like V and W, and if you put this particular correction, so once again it will become out your this type of erratic behavior, and then it will try to reach that particular stable zone. Now, within this particular your erratic behavior zone, so we cannot believe the network, and we will have to believe in this particular range and this particular the range if you want to use this network for making some predictions. So, these are all actually the facts which we should understand if you want to design a very efficient multi-layered feed forward network. Now, I am just going to quickly look into the merits and demerits of this multi-layered feed forward network. Now, so this particular multi-layered feed forward network can handle a large number of variables. Now, if you remember, while discussing the fuzzy reasoning tool, we have already discussed that if the number of input parameters increases and handling or modeling that particular process using fuzzy reasoning tool will be difficult, because the number of rules is going to increase exponentially. For example, say this I have already discussed, if a particular process is having say n number of input parameters, and to represent each input parameter, if I use m linguistic term in fuzzy reasoning tool. So, what will happen? The total number of rules become m raised to the power n. It is a very high number, large number, and this is known as the curse of dimensionality. Now, here for the same problem, if I use the multi-layered feed forward network, so we will be getting efficient modeling. So, in place of this fuzzy reasoning tool, we can use this multi-layered feed forward network. The next is it may not require so much problem information which you need in fuzzy reasoning tool or fuzzy logic controller, because while discussing the fuzzy reasoning tool we have already discussed that its performance depends on the database and the rule base, and if the designer wants to design initially the database and the rule base of the fuzzy reasoning tool, he or she should know or he or she should have at least some initial information of the process to be controlled. But here in neural network training, we may not need so much problem information. Now, based on the experiments, if we can collect some input output relationship, so that you can directly use to train the network, and once it is trained, the network will be able to predict the input output relationship in a very efficient way. Now, disadvantages of the multi-layered feed forward network or demerits. The solution of this the back propagation neural network, that is that multi-layered feed forward network trained using back propagation algorithm, the solution may get stuck at the local minima. So, this I have already discussed, because initially we do not know what should be the nature of the training, nature of the error surface during the training. Now, if the error surface is found to be unimodal, so this back propagation algorithm, which is nothing but the steepest descent algorithm, is going to hit the globally minimum solution very easily. But supposing that the nature of the error surface is such, it is having multiple modes, there are many such ups and downs. So, in that case there is a possibility the solution of this back propagation neural network or multi-layered feed forward network trained using back propagation algorithm may get stuck at the local minima and it may not be able to reach the globally minimum solution. Now, if you see the computational complexity, the training complexity of a neural network and the training complexity of a fuzzy reasoning tool, the training complexity of the multi-layered feed forward network is more compared to the computational complexity of the fuzzy reasoning tool. So, the training of neural network is computationally more complex compared to that of the fuzzy reasoning tool. And there is another drawback I should say, that is this particular multi-layered feed forward network is nothing but a black box. For example, say we have got a set of training scenarios and we train a particular the network. Now, for training what we need is, for a set of training input parameters, what should be the set of output parameters, and if those relationships are known for a large number of training scenarios. So, we can train the network, but during the training what is happening inside the network. So, we the designer we do not know, but ultimately through a large number of iteration. So, it is going to give rise to one optimal or the near optimal network. So, this particular the multi-layered feed forward network works like a black box. Thank you.